Okay, so let's continue our lecture today. So, yeah. Um, okay, so, um, okay, I think last time I stopped this place where I want to use the idea that we borrowed from the unit length case, right? So this is one, this is one, and then this is one. Okay, so uh, okay, so let's see. Okay, so okay, so oh, okay, so yeah, so this is so we are in the unit length case. Sorry, this is not unit length, but yeah, you know what I'm saying. Okay, so okay, so okay, so let's say so if let's say N1 is bigger than N2, right? Um, then what I'm trying to say. So uh, so this is the sum, right? Okay, and then oh, okay. Okay, so okay, I think the idea is that so if we have, let's say N1 is bigger than 3 and 2, right? Okay, let's yeah. So I think I do the case where this N1 is let's say that it's bigger than 3 and 2, and um, then we have, because remember we have the modulus of N1 W1, so that W1 is just equal to 1, so and then N2 W2, so this is minus N2 plus I N2. Yeah, so this yeah. So and then so this term is definitely bigger than or equal to N1 minus N2, right? And then so which is bigger than like 2 and 2, right? Yes. And then yeah, and then wait, no. Okay, so I want to say that N1 plus N2. N1 bigger than 3 and 2. Then N1 plus N2. Yeah, so N1 bigger than 3 and 2. N1 bigger than 3 and 2. And then okay. Oh. Yeah, I think this is true because because we have 304 and 1. I think that's the same thing as the limit idea, I think. Yeah, I think it should be 4. Okay. So then if you move it to here, right? It's actually bigger than wait. Maybe let's keep it 3. I think I made a very nice number, but I forgot. Okay, so okay, let's see how this works. So why? Because 4 over 3 and 1. Okay, so 4 over 3 and 1 is bigger than 1/2 and 2. Oh, sorry. So this is 1 over 4 and 2 plus 1 is 4 over 5. Yeah, so you have 3 and 1 is bigger than 5 and 2, right? Definitely true, because here is 9 and 2, and then this is 5 and 2. So yeah. Yeah. Okay, so so yeah, so in our scenario, so for the general case, right? So I remember that last time we can like without also generality, right? So I think we can just assume that this W1 is like normalized, and then like so W2 is on any like A plus IB, right? Where A is negative, so just like negative A plus IB, right? So where this A is positive, so okay, I think the same algorithm will work here. So right. So okay, never mind. So okay, so how does this? Okay, so let's see here. So for the general case, when you have the expression for W2 as negative A plus IB, right? yeah, so when we are at the general case where this A and B are all constrained, so where um, yeah, so omega 1, yeah, yeah, W2, yeah, negative A plus AB, okay, yeah, and then yeah, so then let me try to think. So in this case, what do I choose my N1? How do I choose my N1? Okay, so roughly speaking, I want what I really want is that I want after I multiply this W1 by this N, right? So okay, so what I want is that. So after I multiply this W1, so I know that W1 has 1, so basically after I multiply this by N1, so it should be bigger than whatever 3 times like this length, right? Yes, so after I multiply by N1, yeah, so and then this, yeah, if I multiply this by N1, so which is just the N1, okay, it should be bigger than 3 times like this total length, right? So this total length, it should be like N2 times A. Okay. Okay, let's see. So okay, so N1 bigger than 3 N2 times A. So okay, so now let's prove that. So now this I have the N1 omega 1 plus N2 omega 2 is equal to just N1 plus minus N2 times A, and then plus I A2 times B. Okay, so this is less than equal to, okay, so actually it's strictly bigger than, okay. Strictly bigger than the okay, N1 minus N2A. Okay. Okay, so can we do the same thing for, yeah, I think we can do the same thing for this one, right? So I argue that, so this is less than, let's say, 1/4 N1 plus, shoot. Okay, so here I need a N1 plus N2. Okay, I think that's a problem here. So, okay, so what do you want to do? So, so, okay, I know that this is definitely bigger than this 1/4 times A times N2, right? So this is for sure. Okay, so Oh, okay. So I think I can just change the constant, right? Because so okay, yeah, because okay, so yeah, maybe I'll use this. So okay, so if this a is bigger than 1 or bigger than or equal to, then this guy is just bigger than or equal to like 1 over 4, right? And then we're done. And then, so the constant is just 1 over 4, okay. So then this constant is just 1 over 4. But if the if a is like less than 1, then what we do is that then so we will have oh, then you just what do I do? So oh, okay. Yeah. So if a is less than 1, then this guy is less than, strictly less than what? Yeah. Right? Because the second term is, yeah, okay. So, yeah, so then we just let the constant to be, okay, so we pick the k to be, so finally, so pick k to the minimum, okay, of, okay. Yeah. Okay, I think we're done, right? Oops, sorry. Okay, so I think this shows the property that okay, so yeah, so this shows the general case. Okay, but the thing is that Uh, okay, so what happened? Okay, so the question becomes, I think we can follow the same logic, right? So, what about this N2A? Okay. Yeah, so what happens if this N1 lies between this N2A and 3N2A? Yeah. So what happens if it is true? So what is the constant here? I think the answer might be similar to this case, right? Where if you have, let's say, okay, let me just read that. So, let me try to get some intuition from here. So, okay, so if let's go back to the unit case. So if this N1 is between this N2 and 3N2. Okay. Okay. So then, okay, because okay, so I think the idea here is that because we know that this guy. Okay, so now we look at the we don't look at this case. Okay, because we know that this is bounded. Okay, this is bounded. So now what we do is that we look at the N2, right? We look at this term, the imaginary part. So yeah, so we use the property that the N1 ratio is bounded, right? So therefore we can bound, yeah, we can always choose a constant that such that the N1 plus N2 is multiplied by that constant is bounded below by this N2. Yeah, we can always do that because this N1 and N2 they are bounded. So this N1 they are bounded within the N2s. Okay. Oh, okay. Okay. So what happened here, right? So what happened in this case, right? I think maybe we use a similar idea here, right? So okay, so in this case, we look at this inequality, right? So then we use this part. Okay. So this is strictly bigger than like N2B, right? Okay, so now the thing is that here this bounds is between like N2A, right? So I think we need to make some change in order to switch from N2A to N2B. So how do we gonna do that? Okay, so how do we do that? So Okay, so I think maybe what we want is that we want to okay, so let's make some change here. So let's do it. Let's divide by A and multiply by B. Okay. Okay. So and then okay. Okay. So what constant do we like to choose here? Okay, so okay, so what we want is that we want to have this n1 plus n2, right? So what we are aiming for is that we are aiming for something times this n1 plus n2, right? That gives us a lower bound, right? So something times this n1 plus n2 that's lower than this n2b, right? Okay, so I know that this n1 over a times b, it must be smaller than this guy, right? So how do I really make? Oh, okay. So let's say that let's just multiply by a over b to see what happens, right? Yes. So okay, so if you multiply this by a over b, and then you have the n1, you have this term appears, right? And then if you divide this whole term by 3, then you know this is gonna be less than because this term is at most, it can't even pass 3 and 2b, right? So if you divide by 3, then it's gonna be less than this and 2b, okay? Yes, okay. So let's see. Okay. If you divide the whole thing by 3, then this term is being made less than this n2b, right? So then the question is, what about this term, right? Oh, okay. So for this term, okay. So for this term, what we do is that we have so this is really b over a times n2, right? So what do you want to multiply it to? Okay, so okay. Okay, so let's leave more space. Okay, so let's leave more space. So say we put a term, let's say 1 over 6 instead of 1 over 3. Okay, so if we put a 1 over 6 in front of this whole thing, then this term is gonna be less than, so this term, okay, so this term, if 1 over 6 is like distributed to here, then is actually less than 1/2. Okay. N2B, right? Yes. So, okay. So now, so if we want to make, okay, so if we multiply, so our goal is to make, okay, so goal, okay, maybe I run in a whole room here. So our goal is to make the other term also less than 1/2 N2B, right? So make maybe like something times over 6 b over a and 2 is less than this. So this term must be less than 1. Okay, otherwise it will break this part. It will break the first part for inequality. So let's say that you have the what's it called? Yeah, 1/2 N2B, right? Okay, so this b actually cancelled out. Okay, and then yes, so we just pick the c to be so the minimum of 1 and yeah, you can even make it like 1/2 or something, but yeah, okay, and then 3a. Okay, I think if you make it 3a, then okay. Yeah, and then this constant will be that. Okay. Okay, so okay, I think we're done. Okay. Okay. Okay, so okay. Okay, so now let's think. Let's go back to our yes. Let's go back to our original case. Okay, so say you have any W1, W2, right? So without any restriction. So so without loss of generality, so after like a rotation, we can always make this W1 to be set towards the x-axis, right? Yeah. Okay, so okay, and then like because in general, right? So yes, here I use the term general case, but in the most general case, so if we have a modulus of n1 omega 1 plus n2 omega 2, okay. So again, like yeah, so this omega 1 and omega 2, let me try to think. Yeah, so basically the idea is that we have a k, right? So we remember that, I think, okay, so we have the k for when the omega 1 and omega 2, they lies in the same, like, right plane. Okay, they both lies in the right half plane. Okay. And then we also have the case where, yeah, we didn't discuss the case where they are perpendicular. So what happens if they are perpendicular? Okay, so if they are perpendicular, yes. So what happens if they are perpendicular? Okay, yeah. So let's talk about the case where they are perpendicular. Okay, so let's say that so when you have a W1 plus W2, what can you control? Okay. Let's fix it. Let's also fix N2. Okay. And then I think we may want to break into cases, right? So if this N1 is n1 less than n2, okay, or equal to. Then okay. Then we just use yeah. So what do we want? Yeah, how do we really find the lower bound in this case? If this n1 is less than or equal to n2, right? Yeah, I think in this case the lower bound must so as low, yeah. So I think the real lower bound is, so if we consider all like the n1 less than equal to n2 but bigger than equal to 0, right? Yeah, but it is right, bigger than equal to 0, but yeah, it must be bigger than equal to 0. Yeah, otherwise it's 0. Okay, so okay, so yeah, so then yeah, so then I think the lower bound will be just the n2, right? Then how do we pick the constant? Oh yeah. So this n1, okay, so this n1 is almost n2, right? Okay, so okay. Yes. Okay, so we just pick the constant to be 1/2. Why? Because if you take the sum, square root of n1 plus, n1 squared plus n2 squared, yeah, so this is bigger than equal to n2, okay. And then okay, and then you have the 1/2 this term, right? Let me write it here. 1/2 yeah. So this term is strictly less than equal to, strictly less than equal to 1/2 n2 plus n2, right? Yeah, so we can bound this one by just n2, okay. Yeah, so therefore, so this is exactly n2, okay. Yeah, so therefore this automatically holds, okay. Yeah. Okay. Okay. Oh, okay. So yeah. So then, okay. Okay. So what happened for if this n1 is bigger than or equal to n2? Okay. So in this case, I think we use the n1 as the upper bound, right? Let's see. Okay, maybe it's a little bit tricky. Okay, n1 squared plus n2 squared should be what? Should be bigger than or equal to n1. Oh, I see. Yeah. So again, we use the same bounds. Okay. So yeah, it should be bigger than or equal to. Okay. So 1/2. Yeah. So we use the N1 as the upper bound. Which is just N1. Okay. Yeah. All right. Okay. So yeah. So we have shown our case. Okay. So then we pick the k to be the minimum over all the sub scenarios. Okay. So okay. So again, like for any N1 and N2, any W1 and W2, right? So no matter whether it's like either positive or negative, right? We can always fit them into one of our scenarios, right? So because, for example, if W1 and W2 they look like that, and then this N1 N2 they are positive, so then yeah, so it fits into this case, okay. And then if this if say that W1 W2 is that, and then this N1 is positive but N2 is negative, right? So then it's like that, okay. So however, okay. Okay, I think the negative case is the same logic. Okay, so okay, so because okay, so you just use yeah, I didn't talk about the negative case. I think you just use instead of B, you use the okay, yeah. So you use the if the negative case, then you make it that. Yeah, what I mean is that if the case that negative, then you just switch the B to negative B, okay. So that the B is still positive, okay. And then but you switch the plus IB to minus IB, where then you ensure that this B is positive, and then we can also do the argument like that, okay. Yeah. So and then yeah. So if it's the negative case, then it falls into one of the negative categories, okay. And then yeah, so what like as long as they are not zero, they are not zero, so we can always find like a matching scenario. So it's one of our scenarios, so therefore they are true, okay, so that shows the general case, okay. Okay, so I think I'm happy to stop today, okay. Thanks.